Hello, this is Connor Hook, and today I'm going to be covering Andrew Foss's problems. And I'm going to be trying to talk a little quicker because apparently I talk extremely slowly. So, in this first problem, we are given some specifications of the Clear Creek River, both in the height drop and in the width at each point. And we're told it's functionally rectangular at each of these cross sections. And we are attempting to find the velocity of a freshman in each of these sections of the river. And we're told he's just going to be going the same velocity as the fluid there. Following along in Andrew's work here, and to clarify, Andrew is not in my group. However, as my group is currently a little bit fractured, I'll be using his work. Using Bernoulli's equation here, and the assumptions are that water is going to be an incompressible flow, and there's no friction for the first section of this problem. We know from Bernoulli's law that the pressure term, velocity term, and elevation term are all going to sum to be a constant, so we can simply rearrange to find this second and third velocity term there, which Andrew does here, and he finds that in the middle, freshman's going to be close to 10 meters per second, and in the last section, he's going to be around 8 meters per second. Pretty fast, but that's why we go tubing Clear Creek, because it's exhilarating. And then we are asked how would this result change, and the Bernoulli equation change if frictional loss was considered, and why is it only an approximation? So clearly it's an approximation because we're not taking into account things like friction and other frictional losses, like a tree branch sticking out in the water. So we're not given enough information to actually solve for the corrective velocities with the friction, but the velocity is going to be lower. And here Andrew used the Bernoulli equation, but adding in the frictional losses to find the velocity down the river. And that covered topic 3, Bernoulli's equation. Next, we are asked to do the balloon animal problem. So there's going to be sections on the momentum balance, the buoyancy, and hydrostatics. First, Andrew just wants us to use the momentum balance to find how much force is exerted on a child, because Sam is a clown working at an amusement park or something like that, and he's going to be blasted with 100 balloons. First, we're going to set up a momentum balance here. The assumptions is that the helium here is going to be steady and incompressible flow, and this stream is normal to the child. I guess he goes through this a lot. What Andrew did here was first note that there's going to be no pressure change, and solving for the force we're actually just going to get is equal to mass flow times velocity. Plugging in mass flow with rho velocity times the cross-sectional area, which are all given, we just get that the velocity term is going to be squared. Solving for the force here, we find that it's going to be about 1/100th of this number, which then Andrew multiplied by 100 balloons to reach around 3 newtons. And he also asks basically how much force is this actually applying on the child, and if the child just let it happen and completely went limp and was just a perfectly floating block, he would move about 8 meters in 10 seconds. All right, so then secondly, we're covering the buoyancy of these balloons. So functionally what we're doing here is we're just going to be finding the volume of the air that is displaced, and that is, according to Archimedes' law, that's basically just a force in the upwards direction, the buoyant force, and we're subtracting the weight of the balloon and the helium, and of course the object, which we don't know the weight of. So assuming Andrew notes that we're assuming no frictional forces here, yes, setting up Archimedes' law, as I stated, we can then calculate that the maximum weight on this object here is going to be about 10.5 grams. It's pretty light, but about right for a balloon. And then lastly, we are asked what the pressure ratio is going to be of a balloon on the surface of a water compared to the balloon 7 meters underwater. So this is using hydrostatics. We're just going to use the rho GH equation. And of course, we're assuming all the classic things like water is incompressible, water has this density of around 1,000 kilograms per meter squared, and so on. Here, we're just going to solve for the pressure at the bottom of the pool. And note that because the balloons are the same volume, this means that the pressures within the balloon must equal the pressure outside the balloon. Solving here, we are now finding that the ratio of the pressure on the bottom to on the surface, which is 0.9 atm, which is given, is going to be about 1.8. So it's quite a bit more pressure on the bottom of the wave pool there. Anyways, thanks for watching, and hopefully I made the 5-minute cut this time.